Okay, we're back. Just to recap, we were in the middle of coming up with the formula for the error and the trapezoid rule, and what we were discussing was that the trapezoid rule does perfect with linear functions with constant slope, but on any particular subinterval, the trapezoid rule does badly when the second derivative is big. But what I possibly didn't explain super well is that this picture of this bad function is one which does agree with the function at the left and right endpoints of the subinterval. So what I drew here is a function which, though agreeing with the function at the left and right endpoints, has a very large second derivative and so produces a lot of error. This is a function which, this purple function is one which agrees with the function at the endpoints but has not as big of a second derivative. And so there's a lot of error. Okay, so if we now go back to what we were doing just as the bell was ringing, what we did was to consider a function. And the function itself is not in this picture. The only sense in which the function is in the picture is that f of 0 is this y value here, and f of h is this y value here. And this, we're going from 0 to h, and so this is sort of meant to be an analysis of a particular subinterval. So we're taking one small subinterval which starts at 0 and ends at h, and what we're saying is, given this particular subinterval, given that the function starts here and ends here on that subinterval, and also given that the second derivative on that subinterval is guaranteed to be less than or equal to k2, what is the worst possible function which still agrees at those endpoints? So what we have done is we've defined this function q, and what is this function q? Q is the function which agrees with f at the left endpoint, agrees with f at the right endpoint, and however has a second derivative which is in fact just q on the entire, which in fact just is k2. So the second derivative of q is k2. In other words, of all the possible things that our function might look like, one function that our function might look like is q. Does that make sense? He gets it because he was in class. Q is, I'll say it one more time, q is a function which might be our function f. Our actual function f is not depicted. And q is the function whose second derivative is constantly k2 over the entire interval. Thus, given the set, given that we have already built into this analysis that the second derivative is capped by k2, q is the worst possible function that might be the actual function that we're analyzing.
But you assume that the constant, that when q, the second derivative of q is constant, that is the worst. Like you assume that any change of the second derivative of q of x, where q of x at some point is decreasing, that makes it a better function. Right.
So our actual function is not in the picture. We don't know what our actual function looks like.
I'm saying that you're assuming that let's say q, that if the second derivative of q of x is at any point less than k2, then the approximation will be a better approximation. Right.
Wait, hold on. I'm not understanding your comment exactly, but what I don't know how good the approximation is per se, right? I'm just wondering by how much could the approximation be off by at most? What's the worst case scenario? As in, without knowing anything more about the function, there's only two things I know about the function, or three things. I know the value of the function here, I know the value of the function here, and I know that the derivative, the second derivative, has to be less than or equal to k2. So what I have motivated, hopefully, is that the function for which using the trapezoid rule will give you the most error would be if the function were in fact the function q.
We've already proven that that's the worst function, right?
I have stipulated, I have sort of tried to explain that yes, this is the worst function. Q would be the worst function.
up to like, how should I say this? I'm sorry. You're saying that if the maximum of the second derivative is k2, you're assuming that the worst possible function is when the second derivative is always that maximum.
Is always k2.
And
exactly. Yes.
If at any point it's less than k2, but like it's never greater than k2, then that function that would not be the worst function.
Right.
Has it been proven yet?
I have not rigorously proven that. You can do some kind of mean value theorem argument to show, but that was what these pictures over here were meant to sort of indicate, right? Is that the more concave it is on that subinterval, the more you're going to be off by using the trapezoid rule specifically. Okay, because that's kind of what the trapezoid rule does, right? The trapezoid rule on a deep level, by sampling the value of the function at the left endpoint of the subinterval and the right endpoint of the subinterval, it essentially assumes that your function is constant. That's kind of the theory behind the trapezoid. No, not constant.
Linear.
Linear, right? Constantly increasing. So if the trapezoid rule is pretending that your function is increasing at a constant rate, the worst function, which can be this value here and this value here, is one in which the derivative is not constant. And the most not constant it can be is if it's increasing as much as it's allowed to increase. And that's what K2 is. K2 is an upper bound on the rate at which the derivative is allowed to increase. I think I've motivated this pretty well, right? Okay, so now we'll just do it. How do we do it? If the green area under this trapezoid is my approximation of the interval using the trapezoid rule, and Q is the worst possible function that f might be, then the maximum area is the difference in those two. And so what we want to do is we want to take the area of the trapezoid minus the area under the Q function. And so that's exactly what we're going to do. We're going to take so that's going to be Q of 0 plus Q of h over 2, so the average of the bases times the height, which is h. That's the area under the trapezoid. And then we're going to subtract out the area under the Q function. And what is the area under the Q function? Well, we did it over there. I guess I could do it again. If the Q function has constant derivative K2, then what does Q look like? Well, its derivative must be K2x plus c, and then the function itself, Q, has to be K2 over 2x squared plus cx plus d. Okay, so now we are just going to do that. So we're going to subtract out the integral from 0 to h of the Q function. Okay, well, that's going to be, I'm going to write kind of small here, Q0 plus QH over 2 times h minus the integral from 0 to h of that function. K2 over 2x squared plus cx plus d. All right, what do we actually get when we do this? Oh, okay, what do we get when we do this? Well, first of all, I'm going to write this as h over 2 here. This Q0 is, in fact, just, what is Q0? Or no, or rather, what is Q, yeah, what is Q of 0? Off to the side here, I can actually compute that. What's Q of 0?
D.
It's just D. Yeah. And what's Q of H? It's just what happens when you plug in H here. So it's K2 over 2H squared plus CH plus D. So the area of this trapezoid, in terms of C's and D's, is H over 2 times Q0 plus QH. Q0 is D, and QH is K2 over 2H squared plus CH plus D. And then we're subtracting this integral, so now I anti-differentiate this again, and I get, so up 3 divided by 3, so that's K2 over 6 x cubed plus c over 2x squared plus dx, and that's evaluated at h and 0. Okay, so now I just have to like do all this crap basically, right? So let's go. Okay, and I'm just gonna multiply everything out. So I have 2 of these d's, so I'll just multiply through. So I have 2 of these d's and I multiply by half, so that's dh plus k2 over 4, you guys check my math, h cubed plus c over 2h squared. That's it, right? Mm-hmm. Okay. And then minus the integral, which is just k2 over 6h cubed plus c over 2h squared plus dh. And hopefully I get a lot of things kind of like combining nicely. So let's see. In fact, a lot of things are just going to cancel, right? This dh cancels with this dh. This c over 2h squared cancels with this c over 2h squared. And my final answer is just k2 over 4h cubed minus k2 over 6h cubed. So this is, what is a 4th minus a 6th? Whatever a 4th minus a 6th is.
12th.
K2h cubed. And yeah, that's like a 12th, right? 6 over 2 24ths. Okay. So, what is it that we have actually done? What we have actually done is to calculate, sort of by brute force, the area under this q function, the worst function, and subtracted it from the area under the trapezoid, which is the basis of our calculation, and we found that the error is, this error is k2 over 12 h cubed. But what actually does that represent in words?
Max error.
The max error possible
Trapezoid.
using the trapezoid rule on just this one subinterval. Remember, this is a picture of just a single subinterval. And so if we actually want the error, the total error on the entire interval, so now I'm going to do the total error. What do I mean when I say total error? I mean the total amount of error produced by using the trapezoid rule at most on that interval. I have to multiply by the number of subintervals, because I might get this much error per subinterval. So the total error is going to be this k2 over 12 h cubed times the number of subintervals, which is n. Oh, and by the way, h cubed was just our temporary representation for delta x to make our algebra easier. So really, really h is like b minus a over n. So we have b minus a over n cubed times n. So the actual grand conclusion of the trapezoid rule error analysis is k2 over 12 b minus a cubed over n squared is the amount of error I should expect. Yes?
But this also means that if you know that a second derivative is constant, you also know exactly how much error is
right.
there.
I don't know the second derivative is constant. This topic is weird because when I say total error, I don't actually mean this is the error, right? Because if I knew exactly how much the error was, then it wouldn't be error. What this really is an upper bound on the error.
But you've proven from here that if the second derivative is a constant, for example, let's say with the polynomial function, then you would know that was the error.
Right.
That's nice. So you can actually use this to get...
Okay, so anyway, hold on. Let's take a look at this formula just like we did in the other video. What we see is, first of all, the bigger k2 is, the more error. That's common sense, right? And because the more, the faster the first derivative is changing, the more error we should expect. The bigger b minus a is, the more error we should expect also, right? The wider the interval, the more error, and in fact that grows cubically. But what's nice now, contrary to the other formula, what's nice is that here we have an n squared in the bottom. So now, as the number of subintervals increases, the error is going to decrease like quadratically. And so now, for a certain number of subintervals, and maybe the good thing to do right now is to turn the camera around and go back to this problem that we were doing regarding finding this integral. The integral, so the problem was, and what we were doing over here is still on the board, we were taking the integral from 1 to 6 of 2 sine 3x dx. And we estimated it using LRAM, and we got negative 0.9285. Okay, so if we use the trapezoid rule, I'm just going to assume that you guys know how to do this, so I won't waste time with it. I did it already. I did T30, and I got negative 1.07718, which is not so different from what I got when I did L30. Okay, but now the real question becomes, how much is this off by? Or not how much is it off by, because that I don't know for sure. But at most, how much can it be off by? Well, now what we need is an upper bound on the second derivative. So if I take my function is 2 sine 3x, and I differentiate this function, I get 6 cosine 3x. If I take the second derivative of this function, I get 18, or negative 18 sine 3x. Yeah? Yeah. Okay, so therefore, what I can say for sure is that the second derivative of this function is guaranteed to be less than 18 on the interval 1, 6. So this number, K2, is 18 in this case. 18 is a nice number that I can say, for sure my second derivative is less than that. All right, well if that's the case, then how much error should I expect? Or how much, or what can I say about the error here? Well, we can just quickly compute it, right? The max error for integrating this function, or the max error for estimating this integral using the trapezoid rule is, according to that formula, it's K2 over 12 b minus a cubed over n squared. In other words, it's 18 over 12. The width of the interval is 5, so we get a 125, but n now is 30. So suddenly I get a 900 down here in the denominator, which is like pretty good. And then, okay, now you have to like do some math real quick. So 3, 2, I can take out like a 25. And how many times is 25 going to 900? Like 36? 25. 36? I think 36. No, that's wrong. Yeah, that's right. 36 times 25 is 900. Yep. So the 3 cancels the 36, that's a 12, so 5/24. Is that even true? Yeah, it is.
That is true.
Yeah, so 5/24. And in decimal form, 5/24 is 0.2083. Okay, well, what is the significance of that? The significance of that is, I can now say for sure that the true integral, without having to worry about where it's concave up or concave down or anything, the true value of the integral is somewhere between this number, t30, so it's t30, basically it's going to be t30 plus or minus 0.2083, which is like pretty good. So t30 minus 0.2083 and t30 plus 0.2083. And combined with this, our computation here, I can say for sure that the true integral is guaranteed to be somewhere between negative 1.2855 and negative 0.8688. Now, that's still pretty terrible, but if you think back to what we did 20 minutes ago, there our error was like 2.5, which is terrible, so this is much better. Okay, the real question, and this is the last thing we'll do then, how many subintervals are required to be sure that our error is less than 0.01? So I'll write that down. How many subintervals are required to guarantee that our error is less than 0.01. In other words, the exact same question we asked 20 minutes ago about using LRAM, which is how many rectangles do I need for this LRAM process to produce error less than this number. Okay, well now, I guess, what do we do? Are you doing it, Alex? So K2 is 18. There's a 12 down here. B minus A is still 125. But now N, we have N squared. And I want to know when is that less than 1 over 100. Now I just kind of solve this quadratic. So 3 halves. I guess I'll just cross multiply or something. What is that? 375. 375, 0, 0. So less than 2n squared. Did I do that right? Yeah. So n squared has to be greater than 187,500. Yeah. And then if you just take this, okay, you guys don't have your calculator on you, but if you just take the square root of
add in a 0.
37, add it, is that too many zeros?
Yeah.
You sure? No, I think that's right.
Look at them.
Oh, so wait, do I need another 0? 3, 7, did I do something wrong? 3, 7, 5, 3, uh-oh. 0, 0, no, you're right, this should be just 2 zeros, so that's just 1 0. So wait, now I don't trust my calculations. Can you, is this right? 125 is indeed 5 cubed. So 3 times 125 is 375 times 100. Yeah, that's right.
That's what I got. Yeah.
So then, yeah, so when can you just divide, can you take the square root of 18,750? What do you get? Square root of 18,750 is 136.9. So n has to be bigger than 136.9. In other words, how many subintervals do I need?
137.
Yeah, only 137. Only 137. Okay, that's kind of awesome. That means that if I want to use the trapezoid rule, and I want to do this particular integral, since this integral has a second derivative which is guaranteed to be less than 18, my error analysis tells me that if I want my integral to be off by at most 0.01, then I need 137 intervals. Contrast that with doing the problem using LRAM, I needed 7,500 subintervals. So this is just much, much better. And the trapezoid rule is great. Only one thing better than the trapezoid rule, the midpoint rule, that will be saved for another day or possibly never. And then there are even more methods which are even more efficient. In other words, that the error is even smaller for a particular number of subintervals. Okay, good. Goodbye. Turning off.